Now let's take a look at SHA 512. 512 here is the number of bits in the output of this hash function. So let me bring up the. Okay, so for this SHA 512, the length small gamma is 512, and capital gamma is really big, which is 2 to the 128 minus 1. Okay, so this is the length. Now remember, this is the length of the input. So your input length could be up to 2 to the 128th power minus 1. Okay, so what we are interested in seeing is the initial value. So it's H0. So this is the initial. We are interested in how SHA 512 defines this initial value for hash code for hash value, and then we also want to know how the compression function is done. So this is Mi, this is H I minus 1. So that is first initial value function. And we also want to know, before that, we also want to know padding. How is M padded? Okay, so these are the things we want to know. It follows the same structure as we saw last time. So this is a cyberblock training mode of F. Okay, so now let me erase this before we move to the next slide. I wish they have a single button to remove all of these. Okay, so the initial value of H0. So this is H0. Okay, it is 512 bits long. So what it does is to uses 8 64-bit registers. So these registers are denoted by R1 up to R8. And the initial value, so these R1, R2, R8. Well, let me just write them out. So write them out. R3, R4, 5, 6, 7, and 8. The initial value is to use the square root of 2, square root of 3, 7, 11, 13. Oh, so this should be 5, right? So it's a square root of the first 8 prime numbers. Okay. 5, 7, 11, 13, 17, and 19. And then the 64-bit digits. The first 64-bit binary digits. Okay, so square root of 2 is 0.14 blah blah blah. So this is an irrational number. So it has infinite many fractional numbers. So you convert that decimal into binary. So you take the first 64-bit binary digits to be the initial values of each of these registers, and then the value of these registers will be updated. That will become the next value of HI, right? So these will be updated. Okay. So now let's see how it is updated. Move them. Okay. So first we pad M. So again, we already mentioned the input length is up to this long, so it is very long. And then the padding here is this. So this is the message M. So what we are going to do is to first so this is capital L is the length of M, and then we are going to write L as a 128-bit binary string. So then I'm going to pad 1 followed by L many zeros, and then followed by this 128-bit long string that indicates the binary value of L. So L is determined by this formula. Okay, so the purpose now is so the purpose now is to make the length of the new string M prime divisible by 1024. Okay, so this is the padding. Let's see how this compression function is done. Okay, so now we are doing the compression function. Excuse me. So each block size is 1024 bits, and each key size, you can think of it, so we have each block is this long, and HI minus 1 is 512 bits long. So you want to convert this into HI, so that is also 512 bits long. Okay, so that is the purpose. So now let's see how these manipulations are done. So So now we have so this H. So this, the current value of these A registers form the value of Hi minus 1. So now we write this block Mi now, which is 128 bits long. I'm sorry, 1024 bits long. So we are going to write it into 16 long words. So there are 16 of them. Long word means each long word has 64 bits. Okay, so this is Mi. Then it generates a subsequent long words W16 to W79 as follows. Okay, so you look at two operations, sigma 0 and sigma 1 here. Sigma 1 is the following shifting and exclusive OR. So this is a shift to the right by 1 bit, to the 8, shift to the right by 8 bits, shift to the left by 7 bits. So the outcome of the 3 shift register. Then you take the exclusive OR, that's sigma 0. And then sigma 1 is doing the different bits. So this right shift 19 bits. This right shift 61 bit. So it will be 61 times, and then left shift 6 times, and also the results will be exclusive OR to get a new 64-bit string. So that is sigma 1. Okay, so then you use a addition. So this is a addition, and after the result, of course, you still want the new result to be 64 bits long. So you take a modular 2 to the 64. Repeat this for T from 19 to 79 times. All right, so that is the first step of manipulation. The next one will be some more operations. So we define X and Y to be either on the bit level. So its bit level will be X1 and Y1. So this is a operation, and this is OR, right? So oops, the definition, just in case you don't remember. So this will be X, Y, so 0, 0, 0, 1, 1, 0, 1, 1, and then there's X and Y, small, and then this is X or Y. So this is 0, 0, 0, 1, and that is 0, 1, 1, 1. Okay. So each of these is a bit level. Okay. So it's just a bitwise AND. This is a bitwise OR. So this is a bitwise negation. This is a negation. So what that means here is X bar is 0, then it becomes a 1, 1 becomes 0. That's negation. So then we define two predicates. Okay, predicate just means this function takes binary, takes inputs of binary values and generates an output either 0 or 1. So this is a CH choose, okay, so X and Y or X bar and XYZ. XYZ is a majority, so this is how it is defined here. And then we also use a sequence, okay, 80, okay, constants. So this constants are K0 up to K79, 80 of them. And then we define two functions, delta 0 and delta 1. Again, more shifts, more exclusive or, okay. Just want to make it so that almost all bits will be scrambled. So now let me erase this. Okay. And move to the next. So now we have this function choose delta 1. This is the constant. Okay, and this is delta 0 and majority. So what it does is take the ACE register, whatever the current value it is a 64-bit, right? So it's 64-bit, 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 and then you add them up, you still want the result to be 64-bit, so you take the modular 2 to the 64. Likewise, T2, you want it to be 64-bit, so after you add these up, then you take the modular 2 to the 64th power. So now we update the values of the register. So R1 will simply be T1 plus T2. Again, you want it to be 64 bits, so you modular 2 to the 64. Okay, and so that is how you are getting HI from HI minus 1. Okay, so now this is HI. All right. Okay, so let me erase this. So you can see better. Right, okay. So now, we let X and Y be binary strings, and we want to define a generalized bitwise exclusive OR operation. So remember, we define exclusive OR sub k earlier when we talk about exclusive OR. So this is equal to A plus B mod 2 to the 64. Okay, so that's what this notation here means, right? So then the modular addition is just this exclusive OR L. So this L is equal to 64. Okay, so now this is the final SHA-512. So we have defined F, okay? We have defined the initial H0. So which, remember, is the initial values for the 8 registers. And so this F updates the values of the registers. And this is not invertible because this MI is 1024 bits. H I minus 1 is 512 bits long, and it generates an output of 512 bits long. Okay, so you add it up with the previous one, take the modulo 2 to the 64, repeat this for n times, and then Hn is the output of your hash code. Okay, so that is SHA-512.